Let's take a look at this related rates problem where we're dealing with a coffee filter. In this scenario, water is dripping through a conical coffee filter at a rate of 11 cubic inches per second. First off, a conical coffee filter would look something like this in the shape of a cone, and we're told that water is dripping through this coffee filter, or this cone-shaped coffee filter, at a rate of 11 cubic inches per second. Next, we're told that the base diameter of this cone is going to be 8 inches, and that the height of this cone is going to be 6 inches tall. So the diameter of the cone, or all the way across the center, is going to be 8 inches long. That's going to be all the way across here. And we know that the height of the cone is going to be 6 inches tall. The question here is, how fast is the water level in the cone changing? At the very instant when the depth of the water in the cone is exactly 5 inches. And here we have our volume of our cone formula. And let's just say that our water level of 5 inches is right about here. Might not be totally proportional here, but just work with it here. Say that's about 5 inches. Alright, so hopefully we can visualize the scenario just a little bit better with this picture drawn, so let's get into the math part. Let's start with our formula, which is going to be the volume of a cone. So the volume of that cone is going to be equal to 1/3 multiplied by pi times the radius squared, which is really just the area of the base, which is a circle, then multiply that by the height of the cone. Now we have three different variables here. We have this capital V, which represents the volume. We have lowercase r for the radius and lowercase h for the height of the cone. Let's go ahead and organize our variables a little bit and see what we're working with and see what we need to figure out. So remember earlier that we were told that the rate at which the volume is changing, so this is 11 cubic inches per second. If it's cubic, that means we're dealing with volume. So if that's a rate of change for volume, then we don't know capital V here, but we do know dV dt, or the rate of change for this volume. So that's going to be dV dt. And that's going to be 11, right? So that's going to be 11 cubic inches per second, so it's inches cubed for every second. Moving on to the radius here, right? We have this r, lowercase r. Now, if we don't know that, we can take a look over here. The diameter is 8, and if that's 8 all the way across, that's the diameter, then the radius must be half, so we're going to go ahead and say that's going to be 4, and that measurement is just going to be 4 inches. Now, as for the height, this one's going to be a little bit more tricky to deal with just because the height is going to be changing as the water is going down in this filter. Now, because we have two different variables on the right side of this equation, let's see if we can maybe find a relationship between them so we can express one maybe in terms of the other. And we're going to go ahead and think back to what we learned in geometry, or maybe even algebra 1 or pre-algebra, in terms of ratios, proportions, and similar triangles. Alright, so let's take a look at this right triangle, which is formed from the entire coffee filter from the beginning, the original one. This is a right triangle, and the entire height of this thing is 6 inches because it's the entire cone from the bottom to the top. And we knew that this measurement right over here from this point to this point is really representing the radius of this cone, or the radius of the circle. So that's going to be 4 inches across. Now let's take a look at this smaller triangle that is formed when the height of the water is at 5 inches. Notice that this is also a right triangle here. This one has a height, or this leg is going to be 5 inches though, and in terms of what is going across here, it should be proportional to whatever this length is over here, right? So the ratio of this height here of 6 to 4, or the leg to the other leg, should be equivalent to this ratio of 5 to whatever this measurement is here, right? And if that helps to see, you can see that this angle does match this angle, and that this angle over here does match this angle over here. So these are called similar triangles, so their ratios or proportions have to be true in terms of their measurements. So since these are similar triangles, then we should be able to say that the ratio of this 4 to 6, I'm going to go ahead and write that down. This ratio is going to be 4 to 6. Go ahead and write that right over here. That's got to be equal to the ratio of whatever this length is here to this 5 that is going up and down here. So I'm just going to go ahead and use an r because it's kind of like a smaller radius, because the circle is a little bit smaller there. And that's going to be a ratio of r to 5 here, right? So this has got to be true. Now, this isn't totally important in the grand scheme of things, but I'm just going to write it out to be super clear, hopefully. If you use cross products here, right, then we multiply 6 times r, that's going to equal just 6r, okay? And that's going to equal 4 times 5 on the other side. Now, 4 times 5, that's going to equal, well, I'll just write it out as 4 times 5. If you want to fast forward, feel free to do so. 4 times 5, and then so we're going to go ahead and write here that this is going to be 6r, or 6 times r is equal to 20. If you divide both sides by 6 here, then what is r really representing? Well, this value here would be r is equal to, that would be 10 over 3, which is going to be 3 1/3, right? So this value right here, we can label in as 3 1/3 inches. Again, not the most important thing here, but I want to kind of emphasize that the ratio of this 4 to 6 must be equivalent to this ratio of 3 1/3 to 5. One of them has a little cleaner numbers than the other, but they do have the same ratio because they are similar triangles. All right, so if that's true, right, we should be able to set up a ratio here of, if we have the radius of the circle and the ratio of that to the height of whatever that triangle that is formed there, then it should be equal to 4 to 6, right? Between the two ratios there, I think 4 to 6 is cleaner or a little bit easier to use than that 3 1/3 to 5. So I'm going to say 4 to 6, right? All right, so let's go ahead and simplify this and clean this up a little bit. So let's use cross products here. If we multiply diagonally, we're going to get 6 times r, and that's going to be equal to h times 4. So that's going to be 4 times h on the other side. So we can think about this in two different ways now. If we go ahead and divide both sides by 6, then we can express the radius in terms of h. So if we do that, we're going to get r is equal to 4h over 6, which just really simplifies down to 2h, and that's going to be over 3, right? So 2/3 and 4/6 would be the same thing. If you also wanted to express h in terms of r, we can go ahead and divide both sides by 4 instead, right? If we do that, then we could say here that the height here would be equal to 6r over 4, or really that's going to be 3r, and that's going to be over 2. All right, so these are equivalent to each other, just different ways of expressing the same equation here. So again, we want to go back to what we were trying to accomplish, which was how can we represent h here? So we know h we can say is equal to 3r over 2. So I'm going to go ahead and write that as 3 times whatever the radius is, 3r over 2. Right, and that would be measured in inches. And we have this other way of representing r as well in case we need it. So let's go ahead and write that down as well. So r, even though we know is at 4 inches, maybe at that given point, that's the radius of the circle. Let's go ahead and see like this r that's going to be changing as the circle is changing. We can go ahead and say that this is going to be 2 times whatever h is, so 2h, and that's going to be over 3. All right, so that's going to be this radius for the smaller triangle as it is changing and the water level is changing. Now let's look back to the original problem to see what we're looking for here. So the question is asking us how fast is the water level in the cone changing? So we're not looking for just a regular measurement here. We're looking for a rate of change. Specifically, we're trying to figure out the rate of change of the water level, and so the given point in time is going to be at 5 inches. So the water level here is really talking about the height, right? So the height's going to be changing with the height of that water level. So we can go ahead and represent that as dh dt. So let's go ahead and write dh dt. So how quickly is the height changing in relation to time? And that's really what we are looking for here in this problem. All right, so if that's the case here, then we really don't want this r in the problem. We don't need it, right? What we want to do is see if we can make a replacement so that we just have h's. Instead of having r's and h's, let's see if we can just have h's here. So good thing that we went ahead and did all this work with the similar triangles, because we can go ahead and replace r with this expression over here to the right of 2h over 3, and then we're just going to have h's on the right side of our equation instead of r's and h's. All right, so let's make some substitutions here. We can say that the volume here is equal to 1/3, and that's going to multiply by pi, and then multiplying by r, but we're going to go ahead and replace that with 2h over 3. So let's make sure we write that as accurately as we can here. So it's going to be 2 times h, and that's going to be over 3. Okay, go ahead and write that in. Then it's going to be this whole thing is squared, right? So let's go ahead and square that, and then multiply by h. And h we know here is going to just stay as h, right? We can just leave that alone. All right, so let's keep going here and see what we get. And we have V is equal to 1/3 times pi here. Then if we go ahead and square 2h in the numerator, that's going to end up being 4 times whatever h is squared. Let's go ahead and write 4h squared. And in the denominator, that 3 times 3 is going to equal 9. So let's go ahead and write that, and that's going to multiply by h. All right, so I think we're making some progress here, but we got to keep on going. If we go ahead and just rearrange and then multiply some pieces together, if we have this 1/3 in front and we multiply that by this 4/9, then we really are going to get 1/3 times 4/9, and that's the same thing as 4/27. So let's go ahead and write that as our part of our coefficient here of 4/27. Let's multiply that by pi. And if we take this h squared and multiply by h to the 1, that's going to end up being this h to the 3rd power. All right, so one final step for this part, if we just do some cleaning up and rearranging, we can say that the volume is equal to 4 pi over 27 times whatever the height is cubed. All right, so at this point, since we just have two variables, we have v and we have h, I think it's appropriate to go ahead and take the derivative of both sides of this equation. Again, we do have a dv dt here, and we are looking for this dh dt. Okay, so let's see if we can go ahead and go a little bit further here. So the derivative of v, or the change of volume, is going to be dv in respect to time. So little change of volume in respect to a little change of time, dv dt. On the right side, let's go ahead and use the power rule. So this 3 can come down in front. We take away 1 from that power. So we're going to end up having a 3 in front. So let's do 3 multiplied by this 4 pi over 27. And then let's think about this h for a moment here. This h here, I'm just going to leave alone. But this is in terms of this h at this given point. So the question is asking about when the height of the water is at 5. So I'm going to go ahead and change this h to this purple color instead. So I'm going to go ahead and multiply by this h, because that's the height that they're asking us. And we're raising this really to what? The 3 minus 1 power, which is really the second power. Okay. Now, after that, don't forget that we took the derivative of the right side, so we also have dh dt on the right side as well, so don't forget to include that. Okay, so let's make some substitutions here. The first one over here is a little bit more straightforward. This dv dt, we knew that the rate of change of the water was 11 cubic inches per second, so we can go ahead and plug that 11 in right over here. We have 11, that's equal to, and then maybe we can do some cross canceling while we're at it on the right side. So this 3 and 27 can cross cancel to make 1 and 9, because 3 is their GCF. And so we're going to end up having what? 4 pi over 9. Okay, so at least that's a little simpler, right? And then now for this h here, this one's a little bit interesting, but the h at this given point is 5, right? If you wanted to use this substitution, this hopefully will also come around and make sense as well, but it would be 3r over 2 depending on what the radius is. Now at this given point where the water level is at 5, the radius here would be at 3 1/3. So if you plug that 3 1/3 in, 3 times 3 1/3 would be 10, okay? And then 10 divided by 2 would be 5. So at this given height of the water of 5 inches, the radius is 3 1/3, and so the height must be 5. So let's go ahead and make that substitution here, that this h value here is going to be 5. Again, that was what the problem was telling us from the beginning here. So we really have 5, and we are squaring it. And then this final substitution is not really substitution, right? We're just looking for this dh dt. So we can go ahead and just leave that as dh dt. Next, we can go ahead and square this 5, so that would be 25. Then 25 times this 4 would be 100. So we'd have 11 is equal to this 100 pi over 9. And that's going to be multiplied by this dh dt. Now to isolate this dh dt, we can just go ahead and divide both sides by 100 pi over 9. That should do the trick in isolating our dh dt, or the change of height in respect to the change of time. So that would be 11 over 1 on the other side, divided by this 100 pi over 9. All right, so dividing that, right, we couldn't plug that right into a calculator and say that this dh dt is going to be approximately equal to 0.315, and that's going to be measured in inches per second. And if you wanted to write this answer in an exact form, you could multiply by the reciprocal here. So 11 times 9 would be 99, over 100 pi. So what did we really find out here? This dH dt is the rate of change of the height of water in respect to time. But that's changing all the time because the radius of the circle is getting smaller as you go down the cone. So the question is asking us, okay, when the height of the water is at 5 inches, what's the rate at which the height is changing, right? So that rate of change is always changing, but at this given point, when the height of the water was at 5, that we know, or we just found out, that it's changing at a rate of 0.315 inches per second, or a little less than a third of an inch for every second. So in conclusion, we can say that when the height of the water is at 5 inches specifically, the water level is changing at a rate of about 0.315 inches per second. So again, it's important to note that at different heights, the rate of change for the water level is going to be different. So this is just specific to when the height of the water is at 5 inches. So there you go, in having a practice problem on dealing with a related rates problem. And this one we were dealing with a coffee filter problem, and there are tons out there. So if you found this video helpful, please consider giving it a thumbs up. And as always, keep up the great work that you're already doing. These problems can definitely be a little tricky. And as always, keep up the great work, and I'll see you in the next one.